The 3 reservoirs assignment is due on Wednesday, and we concluded the second of 2 examples in class on Friday. So hopefully you've made good progress on that assignment. Please upload your files to Blackboard before class time on Wednesday. Today we're going to talk about local losses and get some practice calculating the effective local losses with a Hazen Williams type problem. And then we're also going to get some practice utilizing Moody diagrams, simply because those are included on the FE, and I want you to really be strong at quickly solving Moody diagram type problems. So I emailed out a PDF file earlier today, and if you get a chance to print that, then it'll make these examples a little bit simpler if you can draw right on top of the Moody diagram. All right, so any announcement related questions before we begin talking about local losses? Okay. We briefly addressed local losses in fluid mechanics last semester, and in fact you got a chance to see on the pipe rack some of the fittings and valves and bends that can cause a local reduction in energy. And so in the energy equation, on the right hand side of the energy equation formula is H sub L, head losses. And the 2 constituent components of head losses are friction losses, H sub F, and the local losses, H naught. Sometimes local losses are called minor losses because in comparison to the magnitude of losses that are incurred by friction forces, usually the local losses are relatively small. And so sometimes they're called minor, but I avoid using that lingo because it seems dismissive, and sometimes depending on the velocity of the pipe and how many valves or bends the flow is going through, the losses can be significant. And just as an example of that, I have a water purifier at my house, and the water goes through several carbon block filters and a reverse osmosis filter and several valves along the way, and the water just trickles out of that thing very, very slowly. It'll take 20 seconds to fill up a glass of water through that filter, and it's very pure, good quality water, but there's so many losses along the way that the flow rate is really small. So the way that you calculate the magnitude of a local loss is with a given energy loss coefficient, K. And there are tables of those that are provided by the manufacturers of fittings and valves. And so it's usually a vendor who can give you the data for theirs. And there are tables and references for just in general what types of losses you're likely to experience. But because every gate valve is a little bit different, or every globe valve is slightly different, it's important to get some specific data for the equipment that you're going to be installing or designing at a certain location. Sometimes we have a pipe expansion or reduction in diameter. And here's a picture from the pipe rack in the lab, the fluid mechanics lab. When we were working on the last experiment of the semester doing just that demo, you had both an expansion and a contraction. And you have to be kind of sensitive to the data that you have available, because sometimes if you're calculating the head loss through a diameter change, sometimes the K value is meant to be multiplied by the change in velocity head, and sometimes that K value is specifically calibrated to be multiplied by the entrance or the exit. So here K sub E means the K value for this particular valve is meant to be multiplied by the difference in the velocity head between the inflow and the outflow. But in other tables, it may be just the inflow velocity head that K value is calibrated to. So pay special attention to that. These local losses are because of turbulence that's incurred at just a single location. So we would expect that the water that's changing direction, as it changes direction, there could be some additional turbulence that's incurred even above and beyond the turbulent flow that was experienced just as the water was going in bulk in all the same direction. Entrances where water is coming into a pipe from a tank can have losses, contractions and expansions, including a discharge outlet location where a pipe is dumping into a tank, and so that would also be a location where there's a loss of the velocity head. Bends, where a sharp, abrupt change in direction is going to experience more energy loss than a smooth and gradual transition. And so sometimes the radius of curvature is defined in the K-value tables, so that if the radius of curvature is relatively larger, then you'd have a smaller K-value than if it's an abrupt change in direction. Here is a table that's provided in our textbook, and you can see that for the contraction, both the angle and the tapering of this transition plays a role. So a 180-degree angle would be a very abrupt transition, where essentially you have one diameter connected to another diameter pipe with no intermediate stage where the diameter is gradually adjusting. So 180 degrees would be a sudden contraction, whereas a 60-degree transition would give it a little bit less opportunity for lots of turbulence, and so the K values are much lower for the more gradual change in diameter. And the same thing happens for an expansion, and this diameter 1 to diameter 2 of 0, the ratio of 0 would just be a pipe exiting into a tank. And the same thing here, the first row where we have D2 to D1 is 0. That would be a tank is discharging into a pipe. Okay, here are some typical K values for different types of valves, like a globe valve, a gate valve that's partly opened or full opened. And while these are useful to have in the general case, it's always better to use the manufacturer's specified K values to get a precise idea of the head loss that could be experienced. Here's a table of K values having to do with different radius to diameter. And this is making the point that an abrupt transition, like if you have a 1-to-1 radius to diameter, is going to have a higher K value than a more gradual transition. But then when you go beyond some minima point, you're actually lengthening the bend, and so the K value goes back up again, kind of just as a reflection of the added length of that section. So a radius to diameter of 20 means that you have a really long pipe section making that turn, and so they've kind of just incorporated the frictional losses and the local losses into one lump K value here. That's the thinking behind why the K value is going back up again. Now, why do the K values vary so widely for different types of valves? And a gate value has a particularly low K value because the gate valve doesn't cause much disturbance to the flow when the gate is all the way open. And the gate valve, the piece of metal that would be opposing the flow when the valve is closed, it pulls up and out of the way, so essentially it's an uninterrupted section of pipe and the flow isn't changing direction as it goes through it. In contrast to a globe valve, even when the globe valve is open, the water is coming in, changing directions by 90 degrees, changing directions by 90 degrees again, and then exiting. And so the K value of 10 is partly because it's changing direction, but then also you can look at the diameter of the pipe and compare that to the relatively narrow hole that the water would be flowing through when that plug is up and out of the way. And so there's a reduction in the flow area as well. So, we're talking about an order of magnitude, more than an order of magnitude, 70 times more head loss through a globe valve than you'd experience through a gate valve. Check valves have relatively low head losses depending on how they're configured. If it's a swing type check valve where the gate just gets out of the way, but a ball type check valve is where a little ping pong ball or marble type thing is pushed out of the way as the water's flowing, but it's pushed up against a barrier so it doesn't just flow downstream, and so the water is moving through a small diameter in the case of a ball type check valve. Here is a look at the entrance losses when you have a pipe coming out of a tank, and if it's not protruding into the tank, then you'd have a K value of 0.5, but if the pipe extends into the tank, then the head losses associated with that local loss of energy is even greater. So you'd use a K value of 1 if the pipe extends into the tank. But then if you miter the edges there and make it a more smooth transition, then you could be seeing a K value as low as 0.04 if it's a gradual transition. And then if it's an angled pipe, then that can also contribute to the head losses and increase them above the base value of 0.5. So this suggests that if you take the angle into account, then you can get an idea of how much the head loss increases when it's not only entering the pipe but also changing direction. Here's a closer look at a globe valve and comparing it to a ball valve, and you can see in the case of a ball valve, when that valve is turned, it allows the flow to very rapidly start going through a section of essentially tubing that's identical in diameter to the pipe that's immediately upstream and downstream of it. In contrast to that, the valve plug in a globe valve is just going to be open up maybe as much as it can, but the diameter of flow and the changing direction accounts for why the K values are so much higher. And so Metro Pumps, which is an equipment supplier, has one value of a table of K values available on their website. Oh, I had it pulled up earlier, but then I brought it down. Let me see if I can bring that again just to show you what this manufacturer provided data can look like. The suspense is killing me. I've got so many PDF files in the subfolder. I'm struggling to find it. I guess I'll just download it again. Here we go. All right, so here are the K values that's provided by that manufacturer. The most common valve for residential purposes? Well, I have a gate valve coming into my house. And which one you'd use partly depends on how quickly you need to close it. A gate valve, the gate valve is good because it has very low K value, but it takes a lot of turns to pull that gate up out of the way. So, the valve that goes into my house is a gate valve, but then underneath my sink, I was telling you earlier about the water purifier that I've got. So I have a ball valve going from the water line to my sink. The little branch line to the purifier is a ball valve, and I guess the reason they selected that is so that you could cut it off really quickly. Just with a quarter turn, you can close the ball valve. So the globe valve would be used in a high pressure, maybe more of an industrial environment, where you really could crank down with a lot of force and have a firm seal. The globe valve is not going to leak, so it's good for a high pressure situation. The ball valve leakage could go around the ball, so it's not as good for a really high pressure application. And so I guess probably what's most common depends on the application. Like think about your sink. The sink that you've got that dispenses water in your bathroom, you only have to turn the handle a little bit to get it running. So that's not a globe valve, that's not a gate valve, that's most likely a ball valve that you have at your sink there. Okay, let's take a look at this example to get some calculation practice with local losses. All right, so what we know is the water is flowing from A towards B. We know the elevation difference between A and B is that location B is 12.5 meters higher, and we know the flow velocity is 4 meters per second, and that's going to be useful because here we're using the Hazen Williams method for estimating our friction losses. That speeds things up, right, when we can just use the C value for the pipe directly and not have to bother estimating the F value. Less accurate, but easier. So 350 millimeter diameter pipe, velocity is going 4 meters per second. The pipe is 1,000 meters from section A to section B, so you're going to use that 1,000 meters in the Hazen Williams equation. We want to know, accounting for both the elevation change and the head loss due to pipe friction and the head loss due to local losses, what is the pressure downstream at B? Okay, so I'm going to pause from talking, put you in the breakout rooms to collaborate, and try and calculate the pressure at B. And then we will rejoin to go over that solution and then move on to the next example, which is that practice having to do with the Moody diagram. All right, so give me just a moment and I'll push you to those breakout rooms. For this, let me bring the solution up onto the screen. Okay. Yes. Okay, so I got a good question just a moment ago about that length. You know, is that talking about the pipe length, or is that a plan view length where we need to separately keep track of the pipe length? And even for a relatively steep pipe angle of maybe 10% or even larger, the distance between the inclined length and the horizontal component of the length are close enough that we're not going to differentiate between the two. So we'll use that as the L that goes into the Hazen Williams equation. And when you do the calculations, I hope you got that that's 43.1 meters of friction loss through that section. And then the cumulative K values, if you add up those three locations where you had a fitting, the cumulative K value was 10.4. And so we multiply that by the velocity head using the 4 meter per second velocity that was described, and you'll see that even when there's three successive fittings in a row, the cumulative effect of the local losses is smaller than the friction losses. And now the head loss, H sub L in the energy equation, has the two components, friction and local. So if we rearrange the energy equation to solve for the unknown pressure at 2, so just algebraically isolating P2 here, then we rearrange the equation, we get it's the unit weight multiplied by, now first of all, this is the source of the pressure upstream, was how much pressure there was at 1. So we're starting with 66.26 meters of head at location 1, and then all these things chip away at how much head there is. The elevation difference, because it's an increase in elevation, that means that there's less pressure as you go downstream. So minus 12.5 is the reduction in head because of the elevation difference increasing in elevation at 2. Likewise, the decrease in head due to pipe friction and local losses. So when you add all that together, there's only going to be 2.2 meters of head remaining at location 2. And so that's a pressure of 21.3 kilopascals. And I think earlier in the semester I may have mentioned that we have a lower limit in typical times in a water distribution network. You really wouldn't want the pressure to go below 240 kilopascals, and maybe in an emergency situation like a fire where they're just drawing a lot of water out of a hydrant, it would be okay for temporarily the pressure to get down to maybe 140 kilopascal. But with a pressure this low, there's a risk of backflow into the system where someone opens up the valve of their sink, maybe in a tall building. If you open up your sink when the pressure coming into the house is this low, the water could backflow into the pipe and contaminate the water. So 21.3 kilopascals is the answer to that one, and we've got a little bit of practice with the Hazen Williams and also local losses. Next, we are going to consider two problems. These are the ones that I emailed to you before class to get some practice with the Moody diagram. So we've got 15 minutes for these, and I think that'll be enough time. There's question 1 dealing with water, question 2 dealing with kerosene, and this time I'm not going to put you in the breakout rooms, and the reason why is that when I put you in the breakout rooms you can't see my screen anymore. And just in case somebody didn't get a chance to print this out, I want you to be able to see the Moody diagram on the screen as we work through it. So instead, what I'm going to do is I'm going to put up a poll, and then when you've got the answer to the first one, click yes on the poll, and then that'll let me know kind of the pacing of how quickly people are getting through this. Now remember, for the Moody diagram, what we start off with is the relative roughness on the right vertical axis. We want to find the point of intersection with the relative roughness curve with the Reynolds number that applies. And so here, where it's talking about our flow rate in terms of liters per second, you're going to need to convert that flow rate into a flow velocity. So remember, Q equals VA, so V is Q divided by A. And you can get the A from the pipe diameter that's given. We also know for this wrought iron pipe what's the relative roughness, the equivalent sand roughness coefficient, K sub S. So let me pause for a second and you start working on this scenario, what F value would apply if we're going to then do some calculations with the Darcy-Weisbach equation. Okay, so it looks like most people have indicated that they've finished. Let's take a look at the solution to this one. Let me bring it up. I just scanned it. There we go. All right. So this is water with a given typical kinematic viscosity, and we know the diameter, the equivalent sand roughness, the flow rate in liters per second. We got to be cautious and be sure to convert that into cubic meters per second. The area from the given diameter, and although the diameter is in millimeters, we need it in meters to get the area in meters. And so the velocity 0.177 meters per second, which means the Reynolds number is about 8,000. So 8 times 10 to the third. So that is going to be defining our horizontal axis point, and then the curve is defined by the K sub S to D of 0.001. Okay, so now let's go back to the Moody diagram, 0.001, and here you can see the 0.001 curve, and so it's tricky to follow its path if you're just trying to zoom in on a picture. But if you can, draw with a pencil onto that figure, and it makes it easier to find the interception point. And these logarithmic scales are another thing that in the past I know that students have struggled with in some cases, because there's the temptation to see, well, there's the 8 and there's 10 to the 4th, and so that must mean 8 times 10 to the 4th because it's so close to each other. But that wouldn't be right. It's growing from left to right. So this is 1 times 10 to the 3rd, 2 times 10 to the 3rd, 4 times 10 to the 3rd, and so on and so forth. And then when you get to 9, and then 10 times 10 to the 3rd is the same as 1 times 10 to the 4th. So here the 8 times 10 to the 3rd comes up to our relative roughness curve, and then to the left over gives us 0.034 as the F value. And so, that's kind of an extreme case to have a Reynolds number that low. Maybe you wouldn't see it very often unless you have a very low flow rate, but it ends up giving us a high friction factor that's going to apply in these low flow rate conditions. Okay, so now what about this second one? The second problem, here it is. Kerosene this time. So we've got a different kinematic viscosity. It's a little bit more viscous, more than double the viscosity of water. Is for some reason flowing through a 0.25 meter diameter galvanized pipe at 6.98 cubic meters per second. So this phrase, for some reason, that's my acknowledgement that these flow conditions probably wouldn't be seen in the real world. I just wanted to create a scenario that was at an interesting location on this Moody diagram. So this isn't something that you're likely to see in a real world kerosene pipeline, but let's just go with it and practice the same thing again, calculating the relative roughness, calculating the Reynolds number, and then find the equivalent friction factor F. All right, well, we're almost out of time, so I do want to bring the solution up real quick, just so that we get it on the video if nothing else. And at least one person's calculated it so far, so that's a good sign. Okay, we've got the kerosene, so find the cross-sectional area of the pipe. From that we can get the velocity of flow. The water's going 142 meters per second. That's really speeding along. So that gives us this Reynolds number of 1.5 times 10 to the 7th. We don't maybe appreciate what an enormous Reynolds number that is until we see what velocity is required to achieve it. So for the relative roughness of 0.004, no, 0.0004, I didn't say all of the zeros, then where does that put us on the figure? All right, so here's our high 1.5 times 10 to the 7th Reynolds number. Here is our relative roughness curve, and it's not yet in the curved part. This is the flat part where we're in the rough turbulent zone. So we just go sideways, and it's 0.016. So it would have been that same F value if it was 3 times 10 to the 7th, or if it was 8 times 10 to the 6th. The Reynolds number changing doesn't adjust the F value once you get to the right of that dashed line. Once we're in the fully turbulent zone, then the further increases of Reynolds number does not change the F. All right, that's it for today. We're out of time. It's 1:50 p.m. Hope you're doing well. Remember, assignment 3 is due by Wednesday. Have a great day. If you've got any questions, just let me know. Bye, everybody.